Semantic understanding is a critical building block for everything from autonomous robotic navigation to augmented reality. But there's a persistent problem. Traditional 3D semantic segmentation often relies on closed-set formulations. This means if a model wasn't specifically trained on a coffee machine or a backpack, it simply can't recognize it without costly retraining or new data collection. Vision language models, or VLMs, have largely solved this in 2D. By aligning visual and textual representations in a shared high-dimensional space, models like CLIP and SigLIP allow us to perform open vocabulary segmentation, recognizing virtually any object described in natural language. The real challenge, however, is lifting these capabilities into 3D. Because we lack massive 3D language datasets, most current researchers rely on simple aggregation. They take 2D descriptors from multiple views and just average them together, or they pick one representative view and hope for the best. The problem is that this oversimplifies the embedding. A view of a teapot from the side might show the handle, while a view from the top shows the spout. If you just average those descriptors, you dilute the specific features that make the object identifiable. You aren't capturing a richer semantic whole, you're just averaging out noise. This is where CAMFusion comes in. Instead of treating multiview fusion as a simple aggregation task, the authors of this research reframe it as a semantic super-resolution problem. The core of CAMFusion is a multiview transformer architecture. Rather than just pooling features, the model uses a series of attention blocks. In each block, the embedding for a specific viewpoint performs self-attention, and then cross-attends to a memory containing features from all other viewpoints. This allows the model to actively query complementary information. If one view is occluded or ambiguous, the transformer can fill in the semantic gaps using data from other perspectives to synthesize a single, high-fidelity 3D descriptor. To make this work, the team introduced a novel self-supervised multiview consistency loss. In a standard supervised setup, you'd force the 3D descriptor to match a text label, like chair. But that can lead to overfitting on prototypical classes, causing the model to ignore the actual visual nuances of the object. The multiview consistency loss solves this by forcing the fused descriptor to be predictive of descriptors from unseen viewpoints of the same instance. Essentially, the model is taught that if it sees 5 views of an object, the resulting fused embedding should be consistent with a 6th, unseen view. This encourages the network to learn intrinsic, view-invariant 3D properties rather than just memorizing class prototypes. To further refine this, they added a semantic class mask. This ensures that if 2 different instances of the same class, say 2 different chairs, appear in a batch, the contrastive loss doesn't mistakenly push their descriptors apart. In terms of technical implementation, the system leverages the perception encoder and text region to generate high-quality single-view descriptors. The CAMFusion module then processes these through 8 transformer blocks, ending with a learned latent pooling stage, where a shared latent vector serves as a query to produce the final multiview feature. The results are significant. When integrated with the OVO pipeline for online 3D semantic segmentation, CAMFusion boosted performance from 27% to 38% IOU. In 3D instance classification tests across datasets like ScanNet and Replica, it consistently outperformed naive average pooling and other state-of-the-art baselines, particularly on tail categories, those rare objects that usually trip up open vocabulary models. Crucially, the researchers found that the gap between CAMFusion and other methods is even more pronounced when using ground truth masks. This suggests that the bottleneck in 3D understanding isn't just how we segment the object, but how we fuse the semantic information once we have those segments. While the system is powerful, there are still limitations. It is entirely dependent on the quality of the upstream 2D or 3D masks. If the segmentation is wrong, the fusion will be wrong. Additionally, the current viewpoint selection is based on simple heuristics like mask size, rather than an intelligent selection of the most informative views. Ultimately, CAMFusion proves that multiview descriptors shouldn't be treated as redundant noise to be averaged, but as complementary pieces of a puzzle. By using a transformer to super-resolve these features and a self-supervised loss to ensure consistency, we can bridge the gap between 2D vision language models and robust 3D semantic understanding.